So today what I want to talk about is the gravitational force and how it relates to the centripetal force on an object in orbit. One of the ways that we characterize this, if we consider something like the Earth around the Sun, or any of the planets around the Sun, or the Moon around the Earth, is we started by pretending that it's in circular orbit. So if I take the Earth and I put it in orbit around the Sun, we think about the forces on the Earth, and in this context, there's really only one force on the Earth, and that's the Sun pulling it in. Now, we know that there's a Newton's third law force pair here. That would be the force of the Earth on the Sun. And we know those have to be equal in strength, opposite in direction, and act on the other object. That's part of Newton's third law. We'll actually see that here in a moment. But one of the things we know about the gravitational force as a concept, and this is from a previous study, is that the gravitational force between any two objects can be calculated with g, which is the universal gravitational constant, the mass of one object, in this case the mass of the Sun, times the mass of the Earth, and then divided by the distance between them. But in this case, because we're going to pretend circular motion, the distance between them we call the radius, and that's a square. So this is Newton's law of universal gravitation. What this actually says is that there's a force, gravitational force, between any two objects with mass. And we know that this is a Newton's third law force pair. They're equal in strength and opposite in direction, because if you take mass of the Sun times the mass of the Earth, this would be equal to mass of the Earth times the mass of the Sun. We don't care which one you multiply first. So these obviously have to be the same. They're Newton's third law force pairs, and we're good with that. This is an inverse square law, which means if you doubled the distance between them, doubled that radius, you would decrease the force by a factor of 4. This big G is called the universal gravitational constant, or the gravitational constant of the universe, and it's 6.67 times 10 to the negative 11. Now, it has units, and its value comes from the units. But when we explore the units, we realize that this force on this side has to be measured in newtons. These two have to be in kilograms, and this has to be in meters. So this is what you get here. So if I just do a unit analysis of this, force is measured in newtons. We don't know the G yet. We'll come back to that in a second. This mass is in kilograms. This mass is in kilograms. And this distance is in meters squared. So the question is, what do the units of G have to be so that the newtons ends up on this side and this stuff all magically disappears? Well, it turns out that the units for G are basically the opposite of this. So it's newtons times meters squared divided by kilograms squared. Because if you insert this into this, we can see the meters on top and bottom will disappear, kilograms on top and bottom will disappear, and we're left with newtons equals newtons, which is what we want. If we look at this in a slightly different context, if we say, all right, so now we have this gravitational force formula, which is fine, right? Newton kind of figured this thing out way back in the 1600s. Now, he didn't have a way to measure it, but he had a sense that it was true. If I look at this situation here, if I isolate the Earth, for example, the Earth is in circular motion. And so, if the Earth is in circular motion, is this gravitational force that we see here also the centripetal force? And it turns out it is. So I'm going to set this gravitational force equal to the centripetal force. Now this is a weird thing because we know this equation is G, mass of the sun times the mass of the earth divided by the radius squared. But what is the centripetal force formula? It's mv squared over r. Now what m is this? Well, because we're talking about the earth, this is the mass of the earth. And now we see that some magic happens here with the algebra. These masses disappear, one of these radii disappear, and we're left with, and I'm going to switch the spots here in a moment, we're left with G times the mass of the sun all over the radius is equal to v squared. And so if you want to calculate the speed of an object in orbit around some central body, whether it's a planet around the sun, an asteroid around the sun, or we could switch it if the central body were the Earth or a different planet, but this is for the sun. The speed of any object orbiting the sun is equal to the square root of gravitational constant of the universe times the mass of the sun divided by the orbital radius. This is a really interesting idea. It tells you a couple things. It tells you the farther out the radius is, since it's at the bottom here, the farther out it is, the slower it is. But it's not linear. If you were to double this, the speed would only go down by a factor of root 2, which is 1.4. If you go 4 times as far away, the speed would go down by a factor of 2 because the square root of 4 is 2. So that's a very useful equation. If we go one step farther here, and we have the sense that, well, if you're in circular motion here, and you're in repetitive circular motion, we could say that the speed is equal to 2 pi r over t, where 2 pi r is the circumference of your orbit, and capital T is the period, the time it takes you to go around one time. So what would happen if I took this and I plugged it into here? I would end up with this phrasing here. 2 pi r over t is equal to the square root of g m sun all over r. Now, I'm not good at square roots, so I'm going to square both sides. That becomes a little interesting because you have to square each term. You can't just like square one and hope for the best. So 2 squared is 4, pi squared is pi squared, r squared is r squared, and t squared is t squared. And that's equal to g m sun, in this case, all over r. Now we're doing this for our sun case, but this could be any central body here, it's fine. We see that there's an r here and an r here. 4 pi, g, and m are all constants. So oftentimes you see this like this. You have r cubed, because you had r times r squared, divided by t squared, is equal to g m sun divided by 4 pi squared. And this actually is going to be important for us later. Okay, I want you to keep it in mind now. We're going to have to explore it later in the chapter. But this is a relationship between how far away a planet is in its orbit and how long it takes to go around. But since these are on the same side, one's on the top, one's on the bottom, what it actually means is the farther away you are, the longer it takes to go around, which is a weird way to express this because it's a cube and a square, and we'll have to explore that a little bit later when we get to Kepler's laws.